Howdy.
About the mentor meetings with every other week.
Here.
The email said it was like twice a week, and I was like, wait, what?
Bi-weekly?
Yeah,
Every other week. Bi-weekly can be both.
okay. I
Yeah.
got it.
Yeah. No worries. No worries. Yeah. Good to clarify that. Good to clarify. Howdy.
We need to turn in what we did on Thursday. Okay, I unfortunately left it on my dorm, so I'm willing to take it missing on it.
Okay.
I can bring it in next Thursday, but I imagine you don't want to take late for it.
Yeah.
Okay.
Wait,
That's what
was
this
it
is
work
for.
from work or was it class?
Both.
Oh, so it's both.
Okay, so that.
All work that we do in class is turned in.
Okay. I'm willing to bring it in Thursday then, sorry.
That's fine. Howdy. Any questions before we get started? I don't know. We're gonna be late.
We're still on review, correct?
Yeah, we'll finish up review today, and then we'll start on electrostatics and matter on Monday.
Okay. So we can probably.
Sorry, not Monday, Thursday.
So then we can start reading chapter 4 probably like after today.
Yeah, you should have already reviewed chapter 1, have all that math, review your notes. That'll probably prepare you the most for 4, and then just start, perusing 1, especially polarization. That's where we'll start. Okay.
4.
What? Sorry, 4. Perusing 4, regarding polarization. So we're gonna talk about these just programmatically at the beginning. The first thing to keep in mind is that there is an imminent strike. So if folks have not already talked to you about this, there is a contract negotiation that is completely stalled with CFA. We are asking for a number of different important things as faculty members, because our learning environment is your learning environment, right? So the place that I work is the place that you learn. And in particular, we are looking for some negotiation to get underway, and it's completely stalled. So there is an expectation that we may go on strike in October. And my responsibility to you as students is to make sure your education is well-rounded. So this is why coming to class on time is important, because every minute matters, right? Class starts at 10:30 and we finish at 11:45. So I will start and end on time. And every minute that you miss is a minute that we won't get back, right? The same thing is true of the strike. Every class that we miss is information we will simply not get. And that sucks, because we won't even get through all the stuff that I want to get through this semester. Right? I'm gonna do my best, absolute best, but we will not get through enough stuff, which is gonna suck. Questions before we get started?
How long do you expect it to last?
How strikes work.
Yeah.
Dr. King was like, well, in the past, it's only been today. So,
Yeah, you never know. I mean, if I could give you that prediction, then we would already not be a strike, right? I would never want it to get through. Okay, so you reread the math, you did the problem, and when we stop about halfway through to work on the other problem for today, I will stamp the work that you've already done. Yeah.
can I get one of those?
No. I understand, it's okay, the first one is gonna be fine, we already talked about this separately, but we're not gonna do it in class, right? You're gonna do whatever was done, and I'm just gonna stamp that it was done. Right, so if you didn't bring it in, no. Right, because we'll need to continue working, if you didn't bring it in, then you can't work on the rest of it today.
Is it online or where do I find it?
It's your final.
Problem for, well, yeah, your final for, oh, okay.
Yeah, that was an election. Which you watched, right?
I did watch it.
Okay. Alright. Okay, so here's the Maxwell's equations. Okay, and we're gonna talk about why there's some problems. Anyone know what the problems are with Maxwell's equations? You can just raise your hand if you pretend like you know. I'm not gonna quiz you on. Yeah, you haven't? You know what the problem?
Oh, isn't one of them wrong?
Yeah, one of them's very wrong. Yeah, what?
Yeah,
You know what it is too, right? We're just raising our hands if we know what it is. You see it, right? It's obvious. Right? Okay, so let's find out why it's obvious. Let's start off with a little review of how we get here. Okay, so I promised you that we would do a little bit of the integral formalism today. And you've seen this, especially in fluid dynamics. So there's two fundamental theorems. Okay, this is the first one. And it essentially says that this is not exactly the right part, but let's integrate the divergence over a volume. Okay, so let's imagine that some quantity is diverging. And because I can't draw in 3 dimensions, we're going to use volume and area interchangeably. And then I'm going to use the words area and line interchangeably. And you'll kind of see the difference in my picture. So let's draw a boundary. And let's integrate in this region, okay, over the volume. Okay, that's what this is asking you to do. You see that? Okay. And I'm going to claim that this is the same one symbol. You like that one, right? What's that mean?
over.
Closed surface, very good. All right, so this is some surface or loop if we're working in 2 dimensions, okay? And this is gonna be d dot dA. So what does that mean? That means if I have the same picture, okay? And I have the diverging flux of something, and I take that same sphere, because these are perfectly drawn, right? This is equivalent to starting at some point here and integrating around either the area or the line element, right? And what you'll do is you'll just count up. So we kind of saw this in the last class. But we just counted how much stuff goes in versus out. And this would be equivalent to this. This is the same picture, right? So this is Gauss's theorem. Okay. So what does this mean? So we understand divergence intuitively as how much stuff is going in or out. We're thinking about the example of a hose and you're spraying someone, right? This is in our minds. This is the hose and the water's going out. Now, if I had a hose and an anti-hose in the surface, what would the flux be? 0. Unless the anti-hose was smaller and couldn't absorb all the water, right? Then there would be a net difference in the charge. And then I'd have a little bit more going out than I had going back in. Does that make sense? Okay. Another way of thinking about this is let's look at this room. Okay. We can figure out how many people are in the room by counting how many people went through the door. Right? We see how many people came in and see how many people left, and you're left with the total number of people in the room. So that's what this integral is on the right hand side. Does that make sense? Okay, these are intuitive, right? So even though this looks disgusting, this makes sense. It's just another language. Okay. So now let's talk about Stokes' theorem. Okay. And this is not like how you are at the end of the day, right? Stokes, right? This is a dude, probably. Okay, what does that say? This part here is the surface integral, very good, and we see that that's matched with dA. And then when I draw it on the board, it of course is dl. You can sit here too. What everyone saw. All right, and what's this? Curl, and that means in English? the swirliness, right? So the swirliness of quantity vector V, right? Okay, so how much swirly is going through the surface? Okay, what does that look like? We're gonna show two different examples in a few seconds, but I'm gonna claim that this is the same as this fun thing, and this is gonna be L of V dot dl. Okay, so let's look at two examples again. Now we have some object, okay, like this. How much curly is going through the surface?
No curl.
No curly, right? Why? How do you just see that? I mean, other than intuitively.
Looks more like divergent.
Yeah, it's definitely divergent. Good, there's divergence here. What about this top part tells you that it's zero? That the curl is zero through the surface. What's that?
Normal there's 20.
Exactly. The vectors are normal through the surface. Right? And this is a dot product. So this is asking how much is along the direction of the surface. None of it. Right? This is tangent to it. Okay, so let's do a different example. Now here's my surface, and I'm gonna put some swirly in here. Okay. And maybe there's swirly that goes right along here, right? In this particular circumstance, this would be perfectly aligned. So up here, I would say something like V dot dl equals 0. And here I would say V dot dl equals V. Okay, that's the next. And the real world lives in between. All right, I could rotate the swirly and you get a negative, but it's the same idea. Okay. Okay. So notice this tells us that this thing is going to be, sorry, we do the integral through the integral of the curl along the surface is going to be closed. And that's going to be important when we look at these in the context of E&M. So let's think about this for why we actually care. We talked about water, we talked about all these weird things. This one was Gauss's law. Let's write that this is Stokes theorem here. It's so much better to erase whiteboard with your hand. Some chalk. It's the worst of all time. Okay. So this one is what we have, right? We made this claim. And I'm going to assume that you understand where that comes from last semester. So how do we write that in integral formula? Let's remove some of these fun pictures. So let's write it like this. Make sure I didn't bring this. Okay. So what does this look like? This is saying that if we want to integrate this, where this vector field is now the electric field, okay? We need to find the volume of charge density enclosed. What's that? You want to say that one? Yeah. So this part here says that if we want to understand the divergence integrated over a volume that encapsulates it, we need to think of it in terms of the charge inside of that volume, the integral of that charge, okay, and how it's distributed. Okay. And using this piece up here, we can say something along the lines of E dot dA is equal to Q enclosed over, make a knot, through some surface. It's a very powerful tool, right? Because if the net charge in something is 0, then what does that tell you about the electric field outside of that surface? It's 0, which is really important. Because the reason that my hand does not go through this table is because there are molecular bonds holding, those atoms in place. If every one of those atoms had electric fields, the world would be chaos. right? Because everything else is charged, and suddenly you have all these forces that you have to deal with. So in fact, we live in a fairly neutral environment, which is great. What is an example of non-neutrality that happens in nature, not wires? Lightning. That's pretty violent. It's pretty hot. Imagine if we lived in a world where lightning was just abounding everywhere, right? We'd all be dead, okay? So this is a very convenient thing, that we have net neutrality. In fact, most of the atoms look like this, right? You have a plus and a minus, or maybe 5 pluses and 5 minuses. So the net neutrality outside of the atom is, right? The charge closed is balanced. The enclosed charge is balanced, right? Okay. This is helpful in cases of symmetry. So you can know the solution to the integral very easily. When the electric field is perpendicular to the surface, you know that the electric field is then going to go through that surface area, right? So another way of saying this is, let's look at some specific examples. Okay. Here's example 1. Okay, this is a line of charge. Okay, we have a bunch of electrons somehow on a wire. Okay, so you could use something like this surface, right, which mirrors the symmetry. But it's really important that these go off to infinity, or you build that surface really close, because as you get towards the edge, you're going to get edge effects, and you're going to break the symmetry. As long as you're very far away from the ends, where the cylinder is really close, it's going to look like it has symmetry. Yeah, that's one. What about this one? Let's say you have some plane. How would you build this box? Yeah, right. You'd want to match it, right? Imagine that goes through. Okay. So you build some surface, and then you can see the E field through it. And you say, oh, this is how much charge is in there. Right? Okay. And then the third one that is, fairly straightforward, we've seen it a couple times. You have some charge inside of a circle. Are there other forms of easy symmetry? No, not really. Okay. But for the most part, if you have these geometries, there's already a solution, and you're just finding out Q enclosed, right? Because the part that we care about here, you're going to have this VDZ. So you have some Q as long as it's uniformly distributed. Now, if you had something like this, and the charge is varying along the length, that isn't symmetric, right? Even though it has this geometric symmetry, the charge is varying, which means that you don't have some uniform charge in the middle that you can just pop out the integral, right? Okay. All right, so let's look at B now. Are there ways to solve B? No, I sure hope so. People have more trouble with B or with E? Raise your hand for E. Like when solving equations. For E? Raise your hand for B. Haven't thought about it at all. Raise your hand if you haven't thought about it at all. Okay. So we like honesty, right? Gotta know what we don't know. Okay. Let's look at it. How do we use Stokes theorem? Well, we have an easy way to solve for B. Let's write it again. Well, maybe I shouldn't have deleted it at the top. Shit. All right. Well, let's write it like this. Del cross B. BA is equal to B L. And this is not necessarily a closed surface. This is just a surface. So you'll notice in your book, they do this fun example of a charging capacitor. And we can talk about that more if you'd like, but you have some charging 2-plate capacitor with a wire like that. And there's different ways to draw this surface. So if you drew the surface right here, you get a different answer than if you draw the surface like this, as though that's like an open bag around the capacitor. And we'll see why that's really important in a few seconds. Okay. This thing here is also going to be equal to this fun relationship. what was J again?
Current.
Current density, right. So we have charge density and we have current density. Because currents give rise to magnetic fields and charges give rise to electric fields. That's the symmetry we're seeing here. Okay. And we could say something along the lines of, this it's not right. Integral of P dot dl is going to be mu naught I enclosed. Right? Similarly to the way that we think about charge. But again, we need symmetry. So if we think about this same example here, what is the what does the magnetic field look like for a line? I saw it. What does it look like? Yeah, right? So you need to know the direction of the current, and you need to have a right hand. You don't have to be right-handed, but you need to have a right hand, okay? I can see mostly that that's gonna be okay. Okay, so you're going in the direction of the current, and this is then going into the board on this side and out of the board on this side. That's the symmetry. Is that the case over here? At the very edge of this wire? No, why?
At the edge of the wire?
Yeah.
Doesn't it like kind of lose
Bingo. We need the symmetry, right? We need infinitely long wires, which doesn't exist in nature. But we need the idea of it in order to be able to work these simple problems. What about a sheet like this? Where would you put the loop? Yeah, I need a loop, right? I need this B dot DL to give me the I enclosed in order to figure out where the magnetic field.
Could you just do like the bases of here?
This one here?
Yeah.
Okay, does that enclose any of the current?
Like on, I guess like where it's intersecting the surface.
What's that? So let's imagine that this is a sheet of charge.
Yeah.
Sorry, a sheet of current. This is a sheet of current. Okay, I want to find the B field.
What if you did it perpendicular?
Perpendicular, you like this side?
No.
Which side? This side?
Yeah.
Okay, is this side different from this side? Now, what's the importance of these two sides compared to this side?
It's in plane.
It's not in plane, what'd you say?
The current's going.
The current goes through it. It encircles the current, at least in some part, right? And you'll notice the problem of this one here. Okay, here I built one surface that encapsulates the current, which is going through I, through a discharging capacitor, versus here on the plate, where this surface, the one that goes around it like a bag and has an open hole at the end, does not encapsulate any current. So these would give you two different answers for B field. Call the cops. We broke Maxwell's equation. So something's wrong. Right? Let's go back to that in a few seconds. Generally speaking, when you're doing the integrals in the direction, the notation to keep in mind, and you'll have this in your book, of course, is that it's the thumb in the direction of the current and the right hand rule in the direction of the fingers. So if you're wondering which way, let's say you're going around a circle like this and you're integrating, which way are you supposed to go? Well, it depends on if the current's coming out of the board, the current's going in the board. Okay. We did this one actually. Let's just really quickly. What does the field look like for this? Let's say you have charge or current going this way. What do you mean?
Going that way. The top's going that way.
At the top is going this way?
Yeah. And the bottom's going that way.
All right. Yeah. Right. Okay. Good. So generally speaking, how do we do these types of problems? Okay. Well, depending on whether we need to solve for B or E, there's some steps, right? And we're going to use those steps when we're solving individual problems. Okay. So we're going to look for symmetry. We're going to use Gauss's or Ampere's law, depending on what's appropriate. Okay. We understand that the integrals for B and E can be difficult. Right, these are these ones with 1 over r cubed, and maybe the way that it's written, and all three of the directions. Right, I write this thing L, for example, even though we're going over a volume. So I'm really hiding a lot of really important math here, because this could be a 3-dimensional integral, and they'll suck. Right, everyone knows that. So generally speaking, we want to get to a place where hopefully we can simplify the integrals, and we did this in 2 different ways. Then maybe I'll just write this. Okay. So for B and E, we introduce potentials. Right? How do we write the potential formalism for E? E is equal to
Gradient V.
gradient
V.
V. Is that exactly correct?
Oh, negative.
There we go. Okay, so what is this telling us? So this is telling us that the divergence of V, some quantity V equals E. Okay, so if we thought that we had trouble working with electric fields, let's make it harder. Let's abstract it even more. Right? Does anyone have a feeling for the potential? Oh, I have a great feeling for what that means. No, not always. But you do have a little bit of this for the gravitational potential. And you like the word gravitational potential because you think hill. Right? If I have to walk through the observatory, I know I'm going to be upset. Right? Not just because it's hot, but because I'm going to be tired. It's going to take energy to get up it. So this has something to do, right, with the way that things want to move. This is describing some form of curvature in motion, right? This is going to ask things to start moving. So you say, well, that's good. You know, that's not so bad. So this thing here is a vector product. And this is due to, oh, sorry, not this one. No, the gradient, not the dot. Right? So this is a scalar potential. Okay. This is really nice because this says that in X, Y, Z, I can form this beautiful 3 or maybe 4, depending on how many directions you want to be working in, 12 dimensions if you want to be a string theorist, whatever, right? You can build it from a single scalar potential. Okay, so what's worse? Let's talk about B. Anyone remember this one? Not looks in their notes, remember. It's okay if you don't. I just want to see where you're at. We're in a review, right?
Yes. I think the A.
All right. So here we have the cross product of a thing called A. And of course, you see how good physicists are, right? Well, we had B, so I guess we'll call it A. Right? Okay. So this is the vector potential. Now, why would you want to do this?
Why would we want to use the vector potential?
Yeah. Why would we build it like that? Why wouldn't we just do it the same way with the scalar, like the del dot?
Isn't it because we already know like this magnetic field which is out like some sort of curve and
Yeah, that's an intuitive way of thinking about it. That's certainly the case. But we're also, right, that's the way that you would describe it as a physicist. But as a mathematician, I would say, let's leverage the fact that there is a really cool phenomenon, right? Right? What is this? Yes. Okay. What?
Is that the Laplace or
Yeah, what is Laplace?
Oh, gradient.
Yeah, Laplace is gradient squared, right? This is Laplace. And I'm using A here, but this is just an example, right? Something. If there's something here, it's non-zero, it's Poisson, right? Which we saw for diffusion. This is leveraging the fact that the divergence of the curl is 0, because these are opposite types of vector operations. How much does it go through something is opposite how much it's twisting about. Okay. And so we'll see this when we come to the formalism for combining these in Maxwell's equations. We wrote this. We can also write how we describe V. V is like this, 1/4 pi epsilon naught, integral of rho r prime over r dr prime. Right? And we're going to integrate this all over space. So we are going to find out the contribution of the magnetic field from every, or sorry, of the electric field from every piece of charge in an area on every other piece of charge. Non-trivial, right? Sometimes we can do, and you saw this in your chapter 1 review, you can have image charges. So let's say you have an infinite plane, you can draw some symmetry and just imagine that it's reflected in those different regions. That's okay, right? Importantly, and we saw this in fluids as well, you can have separation of variables. So thank you for making me draw that already. So let's imagine that this is over here, del squared V. And let's imagine that this is not 0, right? Maybe I have some component that is only, that is only going to vary in the x direction. And some other component that's only going to vary in the y direction. Right? So I can write V like this. Writing for this is separation of variables. So del squared V equaling something, gibberish leads to that. Right? In appropriate circumstances. It's not always true, but we're looking for places with symmetry such that we could use that if we needed to. Okay. We've talked a lot about, how to set up these problems. We're talking here about stationary charge giving E. We talked about steady current giving a V. And the class is not, does anyone have a book? What's the name of the book? Electrodynamics. Oh, so that's not static. So what's changing? Velocity is not changing.
Oh,
Something is using velocity. Right. So you could have a single charge. You can move it. Right. The velocity itself doesn't have to change for that to create electrodynamics. Right? You could have constant velocity and you have electrodynamics. Does that make sense? The presence of non-zero velocity is what's changing. Okay. Good. So something has to push charges. And we'll talk about that in detail. How are people's brains doing right now? Do you want to try another problem based on what we've set up here? Yeah. What are you thinking? Okay. I want you to look at 2. Okay, I want you to pair up. I don't want supergroups. 3 maximum, but 2 is preferred. Okay, we're going to take like 15 minutes thinking about what we did here, thinking about how it might be useful, remembering that we did read over the weekend, and this will be one of 2 of the hardest classes you take. Quantum. Guarantee you, half of you will have more of a hard time in quantum, and half of you will have more of a hard time in it. That's just how it is. Every physicist struggles in both.
In both or
in both. Oh no. Both.
Oh.
But one will be harder. Chapter 1.
Oh.
How many are reviewing?
You didn't read it?
I just kidding. Okay. And as I said before, give me your 4 and I'm going to stamp it.
okay.
I need to see what you've done.
Which problem will be working on right now?
You're working on 2, right?
2 right now.
Your name is on
Yeah.
there? You can write this. Okay. Another thing you want to be doing here is not just the outer. I want words. How did you go through the process of beginning to even think about it? This is a blank type of problem. Oh, you guys need to split here. One of you working through it, one of you working through it. No, only if necessary. It's not just because we're friendies, so I can do slightly less work.
No.
The other 2.
Really?
Oh,
row.
Okay, again, more words, right? What is it about it that gives you that symmetry that helps you notice? Right? Okay, yeah, I love these drawings. You have drawings like that, put them in there, right? Put your own version of how you come to some of the ideas and the thought process, but also words. Like understanding where you're going, writing why you're seeing it. Good, I like drawing too. Yeah, good. Right way to go. You can use more complete sentences, not a requirement. I don't mind if you send me, homework that's 15 pages of words. That's great. The much more interesting.
Yeah. No, I still do my backpack and stuff.
Oh yeah, sorry if that is too stampy and ruins your paper.
Yeah. I guess I could write on my own.
Yeah.
So,
I think I did this. We can either do, or like, let's do where the stamps are every, every lecture that we have. Really do.
Well, do some form of a problem. We'll at least set it up, try to work it. Sometimes we won't have time for that, and sometimes we'll just do whatever we're working on. But I think it's, some of the feedback that we got from last semester is that.
Yeah.
And then we can set them up after and more coming together. You have to try them first, right? On two, not days.
that, okay.
Two.
So, for inner, the first and the inner sphere, then.
Yeah, I was like, right now. That's what I was on.
Yeah, that's reasonable.
So, yeah, so we want to look at the.
And you can work on it more after you leave, right? That's why we do it the next day.
Words.
Yeah.
Okay, so the charge density and the inner sphere, we know the. And we know the area is R. So charge density is R over A.
So what means a sphere or a circle? Think circle, but this is sphere. This is spherical symmetry.
I mean, what's the difference between spherical symmetry if you can't see it? Alright, I said, calculate this, consider the spherical symmetry, start charge distribution in the diagram. So the word sphere just implies there's a third dimension in the other page.
And, recall that row. So
Yeah.
we can establish that, we can say, okay, charge over volume. So. Get all certain thing we is the volume that we want to use. So basically, what's the volume? So what is this? And our charge enclosed these are staying in inner sphere of radius R.
I remember
It's using the charge of these, so we already have this. That's the charge enclosed. So this is very close. Or it tells us right here. What charge is. So now the volume side, so what is this? It's leading towards four thirds by R.
Isn't that for the second example, where you use A and B? The answer volume.
Yeah.
So you just drop that in to here, yeah, you still have ground, but then that's our person. Literally just time. You know, to stay, and if we really want to do it.
You put something like this for A, and then do a little bit of that algebra for it.
So in terms of.
Right, okay, so So you're saying, no, here, charge. Plus you said,
Yeah.
so you can find road by getting the divergence.
Sorry, no, by dividing Q and volume. Like, if you know the charge, then you know the whole volume.
I know, I remember charge A and B, but I didn't charge.
Oh, yeah, yeah.
Volume.
That one, you know.
I rewrote it.
Yeah, no, but I'm just saying, this is how you want us to do it, right?
Yeah, by writing
Now
it.
it's-
I don't write.
Yeah.
Oh, okay, so you don't want that,
I don't want algebra.
okay.
It's not an algorithm. You do the algorithm, but it's important to do the algorithm. So one thing to see here, is flip flops. How would I solve this problem?
So, like, let's say for this one, right, like, let's say I didn't do any of that, right, and I only knew how to set up the problem.
Right.
Are we then gonna like this one in class, so I understand how to do the algorithm? Or is it just the algorithm? I feel like understanding it conceptually is a lot. Understanding it by schooling.
Setting them up is what I would do.
Yeah.
Then you go home and you try them on your own, it's gonna be algebra. You see them again, right? You give them back.
Yeah, it's perfect.
And then the.
For these.
For that one. These, the problems that we'll get in class will be. We'll start every problem. And you go home.
Oh, okay. Number one has.
Determining the electric.
But most of reverse every time. So it has. You don't have some kind
Yeah.
Yeah, that's right.
Yeah.
Most of the thing is this guy.
Oh, no, it's done. Maybe it's in high school, bro.
Okay,
So a
so,
bunch of them.
yeah.
I'll read you one that
Yeah.
They're telling you, get a bunch of them involved.
Like, you're like-
Remember the like it's gonna be the same, like break it down with the me, then we can write.
Yeah.
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 Or it actually be a-
Oh,
Yeah.
here.
Yeah.
Yeah, it would be, so, yeah.
Yeah, that's right.
I think you have to take these right up. So if we have one, so then all we care about is ours.
So you use. One.
Yeah.
This.
Yes, we just care about that feature, what we like to do.
And then, doctor, and we wanted in zone 3, this might be.
Yeah, so it doesn't matter, so that's something else that I could point out.
And this is where we would.
And then in zone 4, it's not 0, and then the charge is on the surface. So.
This is, I'm trying to remember how we.
Noise.
This would be zero.
Yeah, so that's like the first thing that they did. For zone 3, there is.
Yeah, they can't.
Yeah, that's why I'm saying zero here because. Since it's insular, I see what you're saying. Yeah. But the.
So.
So we're.
So like, let's know because there's a net
Say.
charge. Net negative charge.
Here.
Yeah, that's the area.
We know that they're.
They could go up there to the entire interior. There's no positive or negative outside.
And on how far you.
Correct?
Yeah.
So it has to depend.
Yeah, so I guess we could write it,
This is the thing, that the capacity for integral, that is part of. It's a very nice thing, that's all I see, the most important. We're sure of that.
yeah, because that's what we want, right? We want a geoelectric field. So there's an observation that we can say about that, so that, you know, that's, so what we're saying.
I'm thinking the amount of time we wait flow.
That's, yeah. Include wind and no wind, we want it, and the wind. And plus, on the other side, you were saying the electric field. And that's what we have to think about. The cluster with the closed surface. So
Yeah.
all that's saying is, okay, all right, under main surface, that's the surface of the sphere there. It's like,
Hey, I guess if you like take the toss to get the surface from the whole thing.
Mhm.
There'd be a net negative.
Yeah.
Q.
yeah.
So that means that zone four up outlets.
Maybe the same.
How would you know that?
Give me surface of square.
I forget.
You're writing down with your friend, right?
I forget, well, we don't do the algebra.
I don't care about the algebra.
No, I know, but with the algebra, we understand how to do, like, how to. Oh,
Okay.
Four fires.
The algebra is not what helps you do it. I don't want you to do that.
So
So you said, correct, you thought of it. Within that charge, there is a field in zone four.
Yeah.
I said, good, how'd you know that? And it's not out, because you didn't do it.
Yeah.
what is it, that's hard to
Yeah.
explain what's happening, without kind of knowing the
Yeah.
algebra, at least in the way I think.
Yeah, you can read both, right? But what I wanna do is I wanna build up that second skill. Because you're right, as you're saying, if you rely on the algebra, that helps you solve the problem. But sometimes starting the problem requires you to think about how to, which algebra to use. So as we build that second skill, we'll get better at being able to use the algebra.
Gauss's law.
Because you have the intuition, it is there. We'll just pull it
I
together.
know that there's some electric field, so we say.
Do we know what zone 2 is? Is it like?
Yeah, it's there, well, it's not.
Or-
I think it's
Then, you know, since it's we can weed it out, and then we can care about what this.
There would be no charges of four.
Would be certified by.
Yeah. Yeah. Well, the insulators like a
We're saying, I guess.
What was that?
We want
The
to.
insulators like a
So that way.
So the charge is fixed,
We can isolate or separate it from this here. So that way it's not. On
Okay, so let's pause here for a minute. Okay. Find a stopping point. Let's talk about how we break this problem down. So it asks three different things. This is roughly the picture, right? And since I'm a really good artist, sometimes I'm gonna get it wrong. Like I'm so creative. So if you see that I did it wrong on the board, you just raise your hand, you're like, actually, Mateo, we do know the charge there. Right? That's what Paulo says, right? But we could say, for example, well, what if we did, like, what if it was like this? What is the charge, or what is the electric field in zone 4? Why?
Because it would enclose all the charge, which is the negative and the positive. And all the
Okay, and you got that maybe from having it intuitively in your head, maybe you read it up here, right? You also used another thing, sort of inherent or inside of yourself. What else did you recognize in this picture? This could be much easier than you think.
Positive and minus.
Positive and negative, yeah, that gives you the Q enclosed equals 0, good. But it's also a symmetric problem. You just saw the spherical symmetry and it clicked right away. But we want to identify the type of symmetry, right? That's an easy statement. Noting spherical symmetry, the net charge is 0, therefore the enclosed charge is 0, therefore the field outside of this is 0. Okay. Imagine a different configuration, one that we don't have here, where you have some lopsided plus and minus like this, and you draw a sphere weirdly through it, right? That can lead to some different problems when they start moving. Here it won't happen, but as long as the net charge is zero. Okay, so let's go back, let's do this problem. Where is there a field? Outside, how do you know that?
We know there's a net charge around the entire.
Good. How did you find the charge in this region, for question A? What did you,
Well, we charge,
yeah, I think A's or problem one.
Charge density.
yeah.
Ask what the charge density is, what you did.
We know that we were giving Q enclosed of positive Q,
Mhm.
and we know that we're dealing with spheres, so we have to do the volume of the sphere, the very first zone, we're given the radius of capital R. So it's, positive Q over four of the green, by off capital R.
Okay, so that already would have given it, right? It would have said, oh, so it's spherical symmetry. I know how to make a sphere. Boom. Okay, so you're good. All right, so zone 4, we know has some field. What happens in zone 3?
Zero electric field,
What?
because it's inside of a conductor. And we know that conductor is next to.
Uh-huh.
And
There's two surfaces. So outside, that's certainly the case. The charge will arrange itself. Right? What about a point right here?
Oh. I'm pretty sure with conductors, like the electric, it should be zero inside of it. That's the outside.
Well, so my question, it's a little different, okay,
Okay.
it's a little different, right? So when we think about this whole thing in here, right? You're thinking about how the charge is distributed. Right, you said it's going to the edges, going to the surface. You're right that the electric field will be zero here. But which surfaces? Where is the charge distributed and how? Do you see it?
Oh, okay, so.
It's a different question, yeah.
What are the negative, the inner circle?
Well, it's negative, the whole thing's negative.
There'll be more negative charge on the inner circle.
Okay, your claim is there's more negative charge on the inner circle. What?
I guess.
Why would it be 1 and 1?
Because it needs to balance out the inside.
The 1 on the inside needs to balance out the 1 here, such that when I'm in here, the net enclosed charge is 0. Because there is no electric field in the conductor.
So
Right?
does that mean zone 2 has a positive, has a negative Q charge?
So that's a good question. Okay, so let's imagine this now. Okay, and we're gonna finish this example in 2 seconds. We're gonna come back to zone 3, but let's think about zone 2. What happens in zone 2? Is there E?
That's whether it comes from that enclosed.
Just what comes from the enclosed charge. So it's Q, right? Is there a field in Q? Oh, sorry, in zone 1?
Yes,
Why?
there is an electric field in zone 1 because there is a charge density in it.
And it's an,
It's,
Yeah. you could just say, right? We're friends enough that we can just, we're spitballing here. We're trying to solve the problem. Okay, so let's go back to zone 3, which I think was giving everyone issues. You said there's 1 Q here and there's 1 Q here. That's the claim. We will disagree with this. We approached it from 2 different directions, right? Your claim was that conductors have 0 E field inside of them. Okay, are these the same claims?
Yes.
Yeah, because if I'm here, the charge has to distribute itself such that this negative charge and this positive charge cancel. That's the property. Okay. And then outside here, you also have 1 Q. Let me ask you a different question. Which one has the higher charge density? Or are they the same?
Which zone has a
No. This surface or this surface? Does this surface have a higher charge density or does this surface have a higher charge density? Or are they the same? So I have same. Right hand for bigger, head for same, left hand for, you do it like this for yourself. Same. Right?
I would assume this is more.
What's charge density again?
Because
Will be smaller. So I think going forward, I think.
You think so? I'm not saying whether zone 4 has more, I'm saying this surface here.
Oh, sorry, the
This-
outer surface.
This surface, okay, outer surface has more charge density?
Yeah.
So let's call this, row 3, 4. And let's call this row 2, 3. Is it like that?
Yes.
Is it like that?
I changed my answer.
Or is it like that?
Absolutely.
Okay, so this middle one, let's see if we can eliminate it. Anyone from middle?
Yeah.
Okay, we got rid of middle. Good.
Bye-bye.
And it's 50-50, so you just flip and you're wrong, right? That's what I do on my homeworks. I would just flip a coin. That gives me the answer, right? Two-face my homeworks. Okay, this one here, does that make sense?
Yes.
Why?
Well, if both surfaces have the same charge, but the inside surface is smaller, wouldn't the inside surface have a higher charge density?
Oh, interesting, right? Because how do we write the word density?
Uh,
That's Q over V.
Yeah.
And the volume is big, the Q is small.
Smaller. Damn.
Is that what you wrote here?
Just thinking.
Hold on. If V is big, rho is small. So which one of these is right?
The bottom. Right? Okay.
Just making sure.
Yeah.
Let's work it through, right? Okay, this is all conceptual. You know, I didn't have to write that. Charge density is words.
Yeah.
Right? I don't have to write V to know that that's the case.
But. So do we agree that like the inner surface has a negative Q and the outer surface also has negative Q? Or-
Oh, it has to, right? There's only Q in that conductor.
But then, if you do the charge enclosed of just the inner surface. There would have to be like a negative Q and a positive Q, wouldn't that just equal 0?
Sorry, say that again?
I just go up and like actually,
You're talking about in this region?
yeah, yeah, it should be in 3, so just taking the charge density of just like the inner surface.
Yeah.
That would have a negative Q.
Yeah.
And inside has a positive Q.
Yeah.
Wouldn't that just equal 0?
Yes.
Okay. But then when we go into like the outer one and get that charge density, there would be a net charge of like negative Q.
Right.
So then.
So what does the field look like outside of zone 4?
It's not be one of negative Q.
One of negative Q. And we know exactly what that looks like, right?
Yeah.
What does that look like? What?
It's like spiritually normal.
Yeah, spherically normal lines. Right, and those are perfectly drawn. In which direction do they go?
For you.
I don't know, you tell me.
Oh, it is negative.
Negative towards
Yeah.
the negative, right?
Yeah.
From positive.
From positive to negative. We're gonna memorize these things. This will become intuitive. I know it's been a summer and everyone's brains all worked, but we're good, right? Questions? This is what I expect sort of in class. Okay, just thinking through the problem. Notice that the work here, the algebra, you kind of have to write, right? It's a tool. But I don't want you to write integrals. I don't want you to work through, okay, the charge density is Q thirds 4, 1, right? That's not as much important in class as recognizing what about the problem tells me how to solve it. Because that will allow you, using this information, to go home, sit down, do the algebra as a tool, as practice, then come back and see if you got it right. I'm not an idiot. There exists some things on the internet that you may have found. Right? Perhaps you just looked and you're like, oh, this homework problem has been solved before. Right? Who would have thought a homework problem has been done? Okay, maybe you asked someone to do the homework problem. Is that learning? Kind of. There is an argument for understanding how the problem is done. If I work a problem in class, some would argue that's learning, right? Is it as good learning as trying it yourself first? No. Does it make sense to help you when you're stuck? I can understand it. I wouldn't recommend it. I can understand it. I think it's better to have a conversation with someone else, but at least I can empathize with feeling stuck and like, where the fuck did I go wrong? Oh, it's this negative sign, right? Is that a substitute? No. If you start reading, say one of these problems, you write it all down, you transcribe it, it will be blatantly obvious. Okay? Because this is not easy shit. And if you don't have an intuitive sense for it, oh, well, I wrote Gauss's law and no other words, I'm going to say no, and you're going to get 0. Right? I need to see your ownership of the material. The world's getting more internet, you know? Does that make sense? Yeah.
About zone 2.
Yeah.
We said that it was net 0 because of the conductor and then the insulator, right?
No. Net 0 is no. No. Zone 2 isn't zone 2 the one that was right outside of the positive here?
Yes.
Yes.
So that doesn't know about the conductor above it.
Oh, that's right. It's the line- yeah, sorry.
It looks like radial lines out to the conductor, right? And interestingly enough, you could imagine a world, I mean, what does a capacitor look like, right? Positive charge, negative charge. How do those lines go? The E field lines near the conductor, right? Just straight across. Really straightforward. So make that circle really, really big. And you would imagine that you have, the separation between them is small, the circles are really big. It's gonna look like a flat capacitor. And guess what? They behave the same way. But you'll get some bending because, of course, they're not flat. So you see that all of the nature, you just kind of change the parameters, you make them bigger, make them smaller, you bend some lines, but they just connect, right? At least for E fields. B fields suck, and we'll talk about that in detail. Okay, questions? Okay, that was almost perfect timing, right? Okay, if we can keep on that type of pace, we'll make through this well. We might get through this a little quick, and hopefully we'll have some time to talk about other stuff. Okay, so what moves the charge? That was my original question, right? Why do people, you have like a abandoned house in San Bernardino, and your buddy calls you, hey buddy, people just moved out. It's like, get into that house and get the copper. Oh, you don't want the copper. To sell it? No, because we're in a physics lab. So we're gonna use it to build a drone. Right, we're gonna build a drone out of it. Why are we gonna build wires out of copper? What the heck is so special about copper? Conductivity? Okay, that's a word. Let's say I don't understand. What about that behind you tells you that this is a good idea to use copper? Is that on there somewhere?
Yeah.
Interesting.
It's a metal and metal.
Yeah. Sorry, say that again, louder for the group.
Valence electron.
Has a valence electron. So what's a valence electron?
Yeah.
What? An outer electron that does what?
Interacts with
It's like moving around. It interacts with its neighbors. So in a metal lattice, it kind of just does whatever it wants. Okay. What? It flows. Yeah, there's some flow. So one thing that and I apologize, I'm gonna delete these and hopefully we don't need them later. You have them in your notes. I'm gonna because I like such pretty pictures and I'm such a good drawer. I'm gonna show you the inside. First time ever, show you the inside of a wire. Yeah. So this is a copper atom. Okay, and if you look at the structure of a copper atom, it has orbitals, right? I think it's like that. There might be a fourth one, but there's one little lonely dude. So this is full, and then this is full. I'm not filling them in, and then there's one. And that's your valence electron. And let's say this is his buddy. Okay. And they are in a copper lattice, pure copper, hopefully. Then these two electrons here, they see each other. Like, what's up, bud? So they're so close that they're like, well, sometimes I'm with you. Sometimes over here with you. Now, does this mean that this becomes copper, negatively ionized copper? No. Because this one says, oh, no, don't worry, I'm out of the house, you stay in my house while I'm gone. Right? It's like a house sharing situation. So it kind of pups around, kind of lives wherever, right? It's a very egalitarian society. Okay, John, can you do me a favor? Can you turn the lights off? Okay, now turn the lights on. Okay, that's pretty quick, right? So he like hit the switch, potential happened. So did an electron from the switch go to here to make the light?
No,
No. What happened?
and just like what happens is that, the wire is like filled with a bunch of electrons, so
Yeah.
you're just like pushing them along, you can push one, push another, and the other.
And that's why it's almost instantaneous. Those wires can be very long. And you can pass them pretty close to the speed of light. Poof, push everyone. You just push them a tiny bit, they push everyone else. So this electron doesn't go all the way to your eye. No.
Well, I guess it's a random question. As when you say like an electron pushes on another one.
Yeah.
I guess I've seen that like even if we had something really long, like we had like a really long like pole.
Yeah.
Like went from like one planet to another, when you pushed it, you wouldn't instantly feel it like at the speed of light at the other one.
Yes,
It
that's the
would be
whole point. Then we are not going to be able to go speed of light, except for anything basically except for light in a vacuum. Everything else will be less than speed of light. But we hit the switch from this giant wire or pole, copper pole that goes to, Alpha Centauri. And we want to send the messages. We lay down some interstellar wire. Right? Still modulated by less than speed of light, because you have to send a pulse. And we'll see pulses first in wires, and then we'll see them in the absence of media. Okay. This is where we're going. Okay, so that's the conceptual idea. Let's break down how it works mathematically. You have something like J, which we've seen before. But I'm going to write it as sigma times a little f. Okay, and this is the force per unit charge. Where sigma here is about conductivity of the material. So copper, good, air, bad. Okay? Air is a bad conductor. Another way of thinking about this would be the resistivity. And that is 1 over sigma. Oh yeah, that's a really cute F. Okay. So generally speaking, this force per unit charge, this could be mechanical energy, this could be chemical energy, but for the purposes of what we'll talk about, we're going to assume that we just have force due to fields. And so we're going to write it as F. What's the force due to fields? E, good, that's the easy one.
Plus, V cross V.
V cross V. Good, it's not V cross V, right? Otherwise,
Back.
you get the wrong direction. Okay, which is fine if you like put a negative. It's not the right equation. Okay. So then we can basically write this in a different way. We could write this as J is equal to sigma E plus del cross E. Okay. I'm not always going to be good at the vectors. You get it, all right? Like writing the little vector signs. I'll try and be good about it, but I won't always be good. Okay. Usually the velocities here, oops, why did I write it like that? The velocities are small. So therefore, you can just write this. Right, you've seen that before. Usually the current is proportional to the field inside of the wire, for example. Let's see, how do we want to talk about this? This is our wire. Okay. You have some length. Delta V. This is our velocity or change in velocity over it. This will be L. And we're going to put some potential here. Okay. So this potential here, so this is an area you would write as the current density J equals I over A. Okay, that's not hard to do, that integral, it's circular, it's a long line of motion. Okay. For the most part, you could write something along the lines of dv, this thing here is ds dotted with delta v. And you can see that from chapter 1, where it shows how to break down those small integrals. But dv, the difference in the potential here, is just minus e over that small area. Okay, so you can write something along the lines of E is equal to delta V over L, more or less. And similarly, you could say that J, let's go back to this example with I and A. J equals sigma E, which we just figured out what E was, is equal to I over the A. Okay, area. Maybe I'll write it that way, so we don't confuse it with the scalar potential. Okay, so sigma delta V. So this is sigma delta sorry. Delta V over L equals I over A. So delta V, if I move all those around, oops, this doesn't even have to over, is L over sigma area times I. Oh, that starts to look legible. This quantity is defined.
Oh, is that resisting?
That is resistive. So Ohm's law comes out naturally when you think about the microphysical structure. Not only do we see it as an empirical law, there's a reason for it, right? Okay. So V equals IR is Ohm's law. That's the resistance for a line, right? It's a function of both the geometry, how long the object is, how wide the surface area is, and the properties of the material, as well as the conductivity, right? Properties of the material. Okay. Maybe we're a little slow. Okay, we might not get to this one, but we'll try. Faraday's law. So now these charges start moving. And these charges start moving along the line. They start generating what? Field, good magnetic field, specifically. That is Faraday's law. So that specifically says that a change in B induces an E field. What? Okay. Changing. That's an I. B induces an E. Okay, let's see if we understand this. Okay. I have some wire. Okay. It's going along and it's fine. Right? I change the current. That changes the magnetic field. And the magnetic field changing creates a back current. What's an example that you've used in your daily life? Might even happen today. Yeah, I have a wire. There's a current through it. It has a magnetic field. What? What happens when you disconnect your phone? Yeah, but in the context of what we're talking about here, this is an example you've seen and heard and maybe felt. Sparks. Let's say you take a plug out of the wall. Why does it spark?
You're suddenly putting off the current.
Yeah, the B field, which is set up by the initial current, goes to 0, which changes the B field, which induces an E field, which is trying to restore it.
That's why it arcs.
Yeah.
Oh, shit.
Yeah. Faraday's law. So you can see this. So we write this in a different way, okay? Minus d dt, okay, of the flux of the magnetic flux, okay, is equal to the fun E. Everyone likes this E. This is the party E, right? This is the EMF, okay? Which is also the less fun E dot dl. Okay. So another way of saying this is that del cross E is equal to minus d dt of B. That's interesting. Sarah, are you a liar?
Oh.
What's the difference?
We're moving.
We're moving. What was this?
Static. Yeah, static.
These are static. This is not. And most of our lives are not static. You know, this is why it's the dumbest class of all time. Because the only thing that matters is light. Light's the coolest. No, I'm just kidding. I say that as an astronomer and planetary scientist who uses light. I'm sure a geologist would be like, statics is the best. And I'm 100% sure that every material scientist in the department will tell me that magnetostatics is the best, but I don't care. Okay, so let's think about it in this context. What does this say? This says that we can, using changing magnetic fields, generate curly E. Okay, all right. This is a quasi-static situation. This is not fully static yet because we haven't gotten there. So we can use magnetostatics to calculate B. And usually, like in lab situations, that's enough to iteratively solve over here. So if you were, not in a quasi-static situation, let's say you have a computer, then you can calculate this at every time. We saw that in computational, where you could like calculate something kind of and plug it in over here and calculate that kind of and see the back reaction. So they're feeding back and forth on one another. Okay, so when we get to radiation at E&M, this will be really important. And this is the reason why light can propagate outside of a medium. Right now, you're hearing me through a medium. What's that medium?
Air.
Air. Light don't care. Light just go. How? Huh? Okay, we'll get to that. All right. So let's write this in a different way. So I told you over here about enclosing fields. I told you that this was broken, right? And it turns out that the thing that we're missing here is located right at the bottom. How do I generate magnetic fields? What's that?
Current moving charge.
Current, very good. What's another way? What? What's another way to generate magnetic fields? So I told you up here that this was fun. This should be adapted. We just said that del cross E can be generated by time varying magnetic fields. So how could I generate B fields? By altering E fields.
Yeah.
Oh, okay. So there's a beautiful little symmetry here, right? We could write del cross B is equal to mu naught J. Same stuff we have over there. But you're gonna add this fun one, which has both of our dudes, mu naught and epsilon naught. Del E, del T. Okay, so does this, oh fuck, sorry, I'm out of time. One last thing, does this solve this problem? Okay, as the capacitor discharges, as flow begins to move from this direction to the other, we said, oh, well, this isn't gonna work because now the charge isn't moving through the encapsulating current. That was only true in a magnetostatic problem, in which case you could use Stokes Theorem in order to just calculate this part, which is the J enclosed. But now you're going to have a changing E field from the changing conductor. And this term here will exactly balance out the changing current, right? So in one phase here, it would be straightforward. You would just see the current through and you would calculate B. On this phase, you would see underneath a changing E. And that changing E through the surface would exactly account for the missing line. That make sense? The loss.
Yeah.
Okay, this is in chapter. The chapter that talks about Faraday's laws. When you reread that same chapter, you'll see the same thing. I didn't make this page. And there's a good description there. Read that a couple times and then we'll talk about it at 2 o'clock when there's the student help session. Not all of you have filled out the surveys. Not all of you have filled out the student help sessions. I put one time in there. Give me a second time, otherwise you just get one.
Oh, we put it in the second time?
What? Put in your availability.